Hi, my name is Nash Bryce. I'm a student at Utah State Electrical Engineering.
I'm Joe Marshall. I'm also a junior in electrical engineering at Utah State.
And this is our project for microcontrollers ECE3710. It is a pen plotter.
So here's a quick explanation of our hardware. This is a weighted bar that has these idler bearings, which then push the paper against these grit rollers. These grit rollers are simply Dremel sanding wheels. And the paper goes through there, and that's what allows the paper to move this way. And then we similarly have a stepper motor with this belted axis, which can move the pen in the X direction. And then finally, there's this bar on a third stepper motor, which is able to lift the pen just a little bit off of the paper so that it can stop writing. You'll also notice we have end stops. The pen end stop is not currently in use, but the other two, these are optical end stops. So you can see this one, as the x-axis gets towards the end, this little flag goes in between the two halves of the optical end stop and triggers it. And similarly, when a piece of paper is in the machine, it does the same with this end stop. So in order to home the machine, you feed the paper in, and then the machine simply moves in the X direction until that end stop is reached, and then moves in the Y direction until that end stop is no longer triggered. That's the mechanical hardware. The electrical hardware is pretty simple. We can just show you on the bottom. So we have our STM32 Nucleo board that we've been using all semester. This is known as a CNC shield. It's mainly used with Arduinos, but luckily the Arduino pin headers are also used on the STM32 board, which makes it easy to connect. And then we have 3 stepper motor drivers, which take step and direction pulses and then drive the stepper motors from that. This wiring is just our end stops. You can see it's a little complicated just because we had to run some power to them. And then this box just takes in AC power, feeds it into this 24-volt power supply, which powers the whole board. And the USB connector on the Nucleo is used to send Gcode commands.
What our microcontroller does is interpret Gcode commands that are received from a Python script on the PC. Now, the way we get these Gcode commands is we get an image, we pass it through Inkscape, and it is able to take the paths of an SVG image and turn those into Gcode commands, which are very simple. They're essentially G00 and G01, draw lines or move the pen tool. G02 and G03, draw arcs, either clockwise or counterclockwise. And then G28 homes the machine.
And any other G-codes are pretty much ignored. They're limited use for us right now.
Yeah, so that's all the Gcode commands we need to draw any image, essentially. Once we get that Gcode command, we pass it to our gsender Python script, which essentially will just send it over UART, over the correct serial port, one line at a time, and then wait to send the next line until it receives an acknowledgement or an OK message from the microcontroller. That way we can throttle the Gcode commands and not overwhelm the system. So here is our Gcode sender. Essentially all this does is it takes the serial port, a baud rate, and the Gcode file that we want to print, and it goes down here, opens the serial port to communicate with the microcontroller, flushes the buffer, and then it opens the Gcode file in read mode, and for each line it'll go through, clean the line. If there's no line, it skips to the next iteration. Once the line's clean, it will write that Gcode line out, and then it will wait for a response from the microcontroller. Here's the response that it'll get. If there's a response, we'll print it out to the screen, and then if the response is okay or an error, we break that while loop, and we just continue to the next line. Then once the microcontroller receives the Gcode command. That goes to our Gcode parser, where it looks at what the initial G number is, so it knows what kind of line to draw. And it'll take the X and Y parameters that are associated with that command and pass them as parameters to that function. And then from there, it's low level, and it draws the line using the steppers.
So here is our code, and then we enter this parse loop command. Now, parse loop, let me scroll up to it, enables the UART communication, and then it just sets the machine's initial state, and then it continually calls this function, which just checks if we've finished the line that we're drawing, and if so, it moves to the next line. If there's any UART characters available to read, then it reads a character, and if it isn't a new line, then it just adds it to the command string that we've got. If it is a new line, then it null terminates that string and parses the command. So you can see in this parse command, it ignores any white space or anything before the start of the command, which is either a G or an M. And then it simply just either calls the G command or M command. Right now, M commands don't do anything. None of them were needed for our application. But G command is where most of the movement commands happen. So we have just a simple switch on the G command number. So for example, if it's G0 or G1, those mean draw a line or move in a line. And so we parse the values for that, the X, Y, and Z coordinates. If the Z is positive, then the pen should be lifted. If the Z is negative, the pen should be dropped. We parse the feed rate, and then we call this write line function, which just puts that line that we just parsed onto the line queue. And then similarly, G2 and G3 are a clockwise and a counterclockwise arc, which behaves mostly the same way. It has a couple more parameters to parse that give us the center point of the arc. But again, it just writes the arc to the queue, and the arc is simply interpreted. It just splits it up into a bunch of lines. And then G21 is another command that we just have to accept but not do anything with. And G28 homes the machine again. So you can see it writes these actions onto the queue. And that's the gist of how our code works. Here's a quick explanation of how the command works to time the stepper motors for writing a line. So we use what's called Bresenham's algorithm. It's normally used in computer graphics to draw a line on a pixelated screen. So for instance, if we wanted to draw a line that was at a slope of 1/3, then what the algorithm does is every single iteration, it moves one in X and adjusts a couple count variables so that on the third count, it will move up one in Y. And then it will simply repeat that and move up another in Y, 2, 3, another, and 2, 3, etc. And doing that, you get the closest pixel approximation to a line in X and Y. We do the same thing, except we don't use X and Y. The X-axis, each pixel, is now one sys-tick interrupt. And then the Y-axis is a stepper motor step. So we'll just increase we have a feed rate for X, our X stepper, and a feed rate for our Y stepper. This is sys-ticks. Let me make that clear. And every sys-tick, we check which stepper needs to be incremented or stepped once, if either of them. So to draw a line in X and Y, we'll actually be drawing essentially two lines in our sys-tick and stepper axis or plane, if that makes sense. Arc commands are exactly the same, we just split them into several lines. And that's how it works.